Till now we have learned asynchronous counters. We have learned 5 types of asynchronous counters, that up counter, down counter, up down counter, and mod 6 counter and mod 10 counter. In up counter, down counter and up down counter, we have learned about the 2 to the power n, mod of 2 to the power n, like this, like mod 4 counter, mod 8 counter, mod 16 counter, such like that. On depend on the mod, we have counted continuously. As the asynchronous counters are used to count continuously. In synchronous counter, basically, why should we go for the synchronous counter? The synchronous counters are counting randomly. Randomness, that in synchronous counter, counts can be random counting also possible in synchronous counter. Also continuous counting is possible, and random counting also possible. So the main advantage of synchronous counter, that is the random counting. Next is that how should we design a synchronous counter? If we follow these 5 easy steps, by following these easy steps, we can design a synchronous counter. That may be for the random counting, that may be for the continuous counting. So for what is these 5 easy steps? Step 1. First, we should decide the number of flip-flop and type of flip-flop that we want to use for designing a synchronous counter. Second step is the excitation table of the flip-flops, that the flip-flop we have chosen for designing the synchronous counter. We should require the excitation table for this flip-flop. Next, for the counting sequence, the state diagram of the counting sequence is essential. That is a step 3, as well as the excitation table of this state diagram. Fourth step, on basis of this excitation table, we should obtain the Boolean expression of the circuit, and the last and fifth step is a drawing the circuit diagram. So if we follow these 5 easy steps, step 1 to decide the number of flip-flops, step 2 the excitation table of the flip-flop, step 3 the state diagram and circuit excitation table, step 4 is a Boolean expression, and step 5 is the circuit design. So if we follow these 5 easy steps, we can design any of the synchronous counter that we will study in this class. Also the next classes we will study different kind of synchronous counters. For the basic and beginning, we should know the basic design of a synchronous counter. So for this we have I've chosen 2-bit synchronous counter for this. So step number one to decide the number of flip-flop and type of flip-flop. So here I have chosen step 1, number of flip-flop 2-bit. So I have chosen 2 flip-flops, and type of flip-flop, for the type, this one is the number of flip-flop, 2 flip-flops, and type as type JK flip-flop. So I have chosen JK flip-flop, 2 JK flip-flop for designing the counter. Because these 2 flip-flop is chosen, as we know from the asynchronous counter design, number of flip-flop equals to number of bits. So here 2-bit, so that I have chosen 2 flip-flop. Step 2, excitation table of the chosen flip-flop. So here chosen flip-flop is a JK. So a JK excitation table. So as we know that excitation table is a PSNS. present state, next state, and JK. So two variables, so four combinations are there. As we know that in the for 0 0, JK 0 don't care, 1 don't care, don't care 1, don't care 0. Next is that third step is a state diagram. So for state diagram, we need to draw the state diagram. So how many steps we should design the synchronous counter can count how many states. It is essential for drawing the state diagram. So here 2 bits, so 2 to the power n, 4 states are possible to count. 4 state 2 to the power n, that is a 4, 2 to the power 2 bits, that is a 2 to the power 2. So 4 states are there. So if we start from the initial 0 0, then first step it comes to the 0 1, second step it comes to the 1 0, third step 1 1, and fourth step 0 0. So 4 states are there. So as decimal equivalent 0 1 2 3. So maximum count is possible 3. We can count 0 to 3. So on basis of this state diagram, we can write the excitation table of the circuit. So that is it is in the step 3. Step 3 first is to draw the state diagram, and second is the circuit excitation table. Circuit excitation table. So PSNS, So here two bits are there. So 2 flip flop. So J0 K0, J1 K1, 2 in 4 in 2 in basically 2 combinations of input. So here PSNS is the 2 outputs are there, Q0 and Q1, because we have 2 flip flops. So 2 flip flop, 2 output. One is a Q0, another is a Q1. So here PSNS also two combinations. So Q1, Q0. Here also Q1, Q0, and here J1, K1, and J0, K0. So 2 variables, so 4 combinations are there. 0 1 1 0 1. So if we can match this state diagram with this circuit excitation table, so first 0 0, next state of this 0 0 is a 0 1. So 0 1, after 0 1, when I am in 0 1, the next step is a 1 0. When in 1 0, present state is 1 0, so next state is a 1 1. And when present state is 1 1, next state is 0 0. So based on this, we can write the J1 K1, J0 K0 by matching this excitation table of JK flip flop. So when 0 0, that is a 0, don't care. When 0 1, that is a 1, don't care. 1 1, that is don't care 0. 1 0, that is don't care 1. Again is 0 1, that is 1, don't care. Again it is 1 0, it is don't care 1. It is next state, it is 0 1, it is 1, don't care. Then 1 0, it is don't care 1. So I have got that excitation table of circuit excitation table that I am going to design. Basically the combinational logic or combinational circuit will form with this from this excitation table. So from this excitation table we can get the Boolean expression of J1 K1 and J0 K0. For J1 I can write the K map of J1 is 4 variables, so I can write the 4 combinations. So for MSP it is Q1 LSB Q0, so that I can write 0 1 don't care don't care. So I can group this. So here 0 1 0 1. So it is the J1 equals to Q0. Next for K1, Q1 Q0 0 1 0 1. So don't care 0 1. Again I can write this K1 equals to Q0. Next is a J0. For K map of J0, Q1 Q0 0 1 0 1. There is a 1 don't care 1 don't care. So we can form one total group. So if all of the variable is formed one single group, then we can write this J0 equals to 1, and now can write for the K0 0 1 0 1 Q1 Q0, and the variable is the don't care 1 don't care 1. So it's also same group by 4. So K0 is equals to 1. Now we have got that Boolean expression. Now next we can design the circuit based on this Boolean expression. So I'm designing the circuit, and now I have got 4 expressions. So J1 equals to Q naught, K1 equals to Q naught, and J0 equals to 1, K0 equals to 1. Now I can design the circuit by using 2 JK flip-flop that I have already I have decided to design the 2-bit synchronous counter, so that I have taken the 2 flip-flop 0. Again next one is the flip-flop 1. So this one is a J0 K0, and this one is the Q0 and Q0 complement. This one is a J1 K1, Q1 and Q1 complement. Now we can connect the circuit, that is J0 and K0 should be connected with 1. So I am taking one logical 1 and shorted logical 1, and Q0 is connected with the J1 and K1, and I am connecting the clock, negative edge triggered clock, and it's a synchronous, so clock is connected to the all flip-flop individually. So I've connected the clock. Now outputs may take from the Q1 and Q0. So this one is the LSB Q0, and this one is the MSB Q1. This counter can count 0, 1, 2, 3. This is a mod 2 synchronous counter. Mod or 2-bit, sorry, mod 2-bit synchronous counter. Thank you.